Hello, I'm Harshvardhan. Today, I'll present our work, a seamless second factor verification as a mobility service for the future commute stations. This is a collaborative work between Singapore University of Technology and Design and Silence Laboratories, Singapore. Urban mobility and ride-sharing services have witnessed exponential growth in the past decade. But with this increase in usage, the frauds have increased too. These frauds take different forms. They can be fake drivers, fake locations, and fake rides as well. These industries incur loss in refunds of fraudulent claims. The major reason for these losses is the lack of evidence about the trip completion. Currently, there's no system to collect these evidences and verify these claims. To solve this issue, we propose our system ProofRide, which asks one question: can we do a hassle-free verification of claims? ProofRide acts as a usable and silent second factor solution and proof gathering mechanism for mobility service companies. It helps in verification and accumulating of evidences to counter fraudulent claims. The basic assumption of ProofRide is co-located devices in a vehicle in a same trip would observe very similar event sequences and time differences. By event sequences, I mean the motion state such as starting, stopping, or cruising of a vehicle. We also consider the magnitudes of these events. Let us see how ProofRide works. Suppose a passenger wants to take a ride. Post-booking, ProofRide server matches him to one driver. When the trip commences, the ProofRide server pulls sensor inferences from both driver and passenger's mobile phone. Based on the length, the type of the route, and the type of the vehicle, the trip duration is estimated. The ProofRide server then queries IMU sensor inferences from both driver and passenger devices based on this estimate. The server processes these inferences from these sensors and validates the claim. To validate our basic idea, we had two questions to answer. The first one, do devices present in one vehicle experience similar events? And the second, do different trips on the same route generate different event sequences? The answer to the first one was quite trivial. So we investigated the second question in detail. We studied randomness in the event sequence of multiple trips between location A and location B as shown in the map. As shown in this figure, for the exact same route, there were different event sequences for each trip. So I've shown 5 trips here. And to be more specific, the occurrences of time of each event on each trip was different. The number of each event in each trip was different. And even the duration of each trip was different. We also performed niche tests to validate our observations. So ProofRide can be divided into a number of modules, such as the mobility event detector, the event encoder, and the co-location verifier. The mobility event detector has 2 roles: the motion state detection and vehicle turning estimation. The motion state detection detects whether the vehicle is starting, stopping, or cruising, as I explained earlier, and records these events with timestamps. The turn detection records the magnitudes and timestamps of each turn taken. So I'll go in detail about the motion state. So the motion state detection takes the input from IMU sensor data and employs basic machine learning model to detect the states. We had to address a few issues, such as the location of this device inside the vehicle, the noise introduced by motion of the passenger, and variability of the device while developing the module. To estimate the turning of this vehicle, the process is twofold. We first continuously estimate the device rotation. Second, we opportunistically estimate the cruising direction of the vehicle. Let us take an example here. So this graph here explains like the IMU readings of the instance when a vehicle actually took a turn. And for the cruising direction, we opportunistically choose instances where acceleration is decent enough and gyroscope has low values. The acceleration needs to be decent because the cruising direction is actually derived from the acceleration, and the low value of gyroscope ensures that the cruising direction is stable at the instance when we are getting the cruising direction. So the purple line in this graph represents the resultant value of continuous rotation estimation. And it tells us here that the vehicle took a turn. The orange dashed line shows that the resultant of cruising direction is also validating that the turn was taken. And then there's the verifier module, which is responsible for matching event sequences on the server. If you want to know a bit more about this and the event encoder module, please refer to our paper. In this paper, we also defined two fraud models, an active fraud and a passive fraud. Active frauds are the frauds where an adversary who knows the inner working of the proofread system intentionally injects noise to corrupt the event sequences by physically moving their device. Passive frauds are those where the adversary makes false claims without actually changing the event sequence or corrupting it. So here we have to address one important question. Can an active attacker actually alter or inject turns into the event sequence? So the answer is yes. An attacker can introduce rotational disturbances to insert or negate turns. For example, in this figure shown here, while the vehicle moves in a straight line, the attacker can rotate his phone and inject a turn event. So how do we prevent this attack? The catch here is that heading direction cannot be altered. So here in this image, we can see that the image shown here gives us an instance where the vehicle actually took a turn, but there was rotational disturbances introduced by the attacker, and the resultant of this module shows that the turn got negated. So even though the rotation estimation did not detect a turn, we still observe change in heading direction, and thereby we detect the turn correctly. So for our study, we collected data in 10 cities spread across 5 countries using 4 modes of transport and across more than 500 kilometers. The first figure in here depicts the accuracy of matching event intervals for start and stop events. And the second figure here depicts the same for turn events. Our event detection algorithm has an accuracy of 96% on average with a false positive rate of 5%. The accuracy is 94.1% for bike trips and 100% for metro train trips. The active attack can be detected by our model with an accuracy of 93%. The first figure here depicts conditional entropy of path with respect to other paths. And the second figure here depicts mutual information between secrets from different trips on the same route. So here we prove that secrets generated by these events are random enough as the conditional entropy is high, even for the same route with different trips. So like the same route, but trips taken at different time, mutual information is very low. So these results show that it is very hard to perform a passive attack. By using proofread, loads of services can be provided to a passenger, such as login to onboard content delivery, targeted suggestions on promotions and offers, peer-to-peer communication for on-board gaming or sharing. To summarize, we propose a seamless system which acts as a second factor of verification and proof gathering. We also design a signal processing pipeline to identify and mitigate frauds. Thank you. That's my presentation. For more details, you can refer to our page.